Hi, I'm Wayne Sherman. I had a great experience at Buick and GM Powertrain. My experiences were kind of neat because I hired into the engineering specifications group initially and worked there for a number of years. And I had expressed to my management the desire to become more or less a development engineer. I was pursuing an education at the time, which General Motors was doing everything but standing on their head to facilitate. And because of that facilitation of my growth as an employee within the organization, they were moving me under the tutelage of some of the, what I would consider to be some of the best minds in the business. And I, because of that, was able to grow and develop with those people. You may have heard of people such as Vince Piggins, or, you know, from Chevrolet. You've heard Herb Fischel. I think of Joe Negri. Ron Ewell was a fabulous manager. I had opportunity to work for Ron. Dennis Manor. Denny is the boss. And then under Dennis, we had the base engine group. And under those three managers, I spent a lot of time. And it was under those managers that I had to carry out certain projects, whether it be running engines in offsites, whether it be dealing with the vendors, whether it be going out and running vehicles and finding out what was really going on. I also want to thank Bill Owen because, and he's sitting right there prompting me. I just want to say Bill is an awesome guy in terms of taking engineering concepts and making them real simple. And if you stood around and talked with him for a while, you would see that. But what I wanted to share with you folks this morning, or this afternoon, had an opportunity over the years and through just my experience with the organization to stumble on things within the Buick powertrain that enabled people, the newbies, if you will, to find a little more pony here, a little more torque there, make it run a little better. And I don't want to imply that I am going to tell some of you folks here that run 9 seconds or whatever you're running that I know something that you don't. I'm trying to share a few minor things that might help the newbie, might help somebody that may have never seen this stuff before. And they're there. It does exist. For example, what we know in the beginning, fluid dynamics shows that short, straight cylinders, or tubes, if you will, have the least flow energy losses. Turns should have smooth radius. Corners and abrupt diameter changes are not friendly. High underhood temps rob performance. For example, a street car might run 130 to 180 degrees Fahrenheit, but a track car could be much worse. Generally, a 1% horsepower gain for every 12 to 15 degrees Fahrenheit temperature drop is possible. What we would like to have, we should all have short, straight ram tubes furnishing cold laminar air. Well, we can just dream on. For any of those who could still possibly have a stock turbo, for example, break the edge inside of the inducer, not in the compressor housing, that little edge in there. Don't touch the housing. Now my now it's not going. We had it moving on top to bottom. We had it moving up and down last night. What was it, top? Yeah, and I don't know, it wouldn't go. Right there, that button. Oh, you got to go down. The air induction plumbing, for example, I'd like you to look at, this is a drawing that I did just to show you corner airflow versus laminar stable airflow. On the left, what you might be able to see is a projection of that non-stable air in that yellow area inside that inside the tube there on the left. And if you notice on the right, there's an increase in the laminar flow. In other words, that yellow area gets thinner. This is a representation, more or less, of a typical air filter that we would use on a Grand National in this day and age, or a Turbo Trans Am. The filter surface area and proximity to the amount of air are also ambient air are also major factors. I'd like to thank Doug's Fast Z. I talked with him or sent him emails and asked him if I could use a couple of his photographs. For example, here we can take some of the casting flash out of the compressor output, out of the outlet, and a Tootsie Roll is a useful tool to clean that up. We don't want to mess with the nozzle or the outlet size, but just a general smoothing, if you will. The turbine housing is quite an amazing piece of hardware. You can see on the left we have a housing that has been massaged. You can't see it very well in this picture because the texture inside of the port is not obvious. On the right, you can see the witness from the exhaust manifold, and that witness kind of gives us the idea that we have some sort of reversion. We can gain a little bit of flow velocity and total flow at some unit of time through that port by blending and working to that witness mark. We don't want to have any gas reversion, as I've got in here, and it will improve our cross-sectional flow area. A lightly blended wall just past the puck hole is also necessary to control the gas coming out of the housing so that we can put a puck on there and control our boost. If we smooth that area off too much, and you can't see it in the picture, I can see it on my laptop. If we don't have enough area out there, we really don't create enough of a wall to drive air out through the puck when the puck comes off the surface. We would like a hole with a margin of about 1/8 of an inch, depending on the puck size, but a typical aftermarket turbocharger gives us that opportunity. And we do have to seat the puck over the hole. We need to leave the nozzle alone. If we mess with the nozzle, then we mess with the targeting of the exhaust gases, and we also mess with the velocity of the exhaust gases being targeted. This is a slice of a turbine housing. And this is, and I'd like to thank Tom Halka, by the way. Tom worked with me for about 3 or 4 hours last night, and we went through this, and we changed some things at the last minute just to make this a little easier. Some turbine housings have shown flash or excess material slightly impeding the gas flow through the housing slot. What you have in a turbine housing, the gas comes up, it scrolls around, and you have velocity. What you want to do is you want to create enough pressure to drive that gas through the slot and then down to the wheel. If you have casting flash or interfering material in there, that messes with the gas going down to the wheel. You can actually go in there with a very, very small stone and like a Dremel and clean that up. That is an opportunity to get your spool a little better and maybe even make a little bit more wheel speed. The condition, like I said, it can be resolved with a small die grinder, and the stone itself is actually captured inside of the turbine housing when you do the work. So you actually have the die grinder and you put it up to the slot, and then you collar in the stone. You can see there the shape of the. If you look at the bottom, you can see the blades from the turbine wheel right there. There's 2 of them at the bottom, and I tried to exaggerate the size of the slot there so you can see that the exhaust gas is coming from the slot or through the slot where the arrows are to the lower arrow there where it says exhaust pressure. The exhaust manifold is an interesting piece of hardware because winking occurs typically in runners 2, 3, 4, and 5. We may be able to, I'm trying to make this a little easier to see, but I don't know whether I can. Oh, joy. There it is. Winking will occur, I already read that. The metal flow may be a little high at any flange to runner joint, and caution should be exercised as to not to damage the weld joints which are at the inside of the runner. But what I mean by that is there is an inside weld at the exhaust flange. The runner runs right up there, and the weld was done inside the flange. Sometimes there's some high material in there. You can go in there with a stone and just trim it out. And you can see also as well, what I tried to do is I tried to do a slice of the exhaust manifold, and the green area is the log. The white lines indicate the runner. This is just very, very simplified. There's no dimensional integrity or implication here other than to show that the area where the green radius meets the runner is shown in the left view there, and what we want to do is we don't want to have that green area there because now I could be blocking flow out of that runner into the log. We have the driver's side exhaust manifold off of a typical production car, and you can see some of the witness mark here on there's two circles. There's an inner circle and there's an outer circle. The inner circle is not being contacted by the donut. So we can eliminate some of that, and we can possibly get a little more flow out of that manifold. You can also see where the runner meets the collector, and it's pretty hard to see, but up in the top right corner, you can see some weld material in there, some material that is probably blocking that flow. That looks a little more reasonable, and basically you've pretty much maximized your flow without damaging the piece, which, like I said, you want to follow the witness marks and be very careful. In the passenger side exhaust manifold, there's an O2 boss in there. Typically, we can trim that down. I don't recommend going crazy on it. The other option as well is to do that and use a competitor, a Nippon Denso 234-101, which has a smaller body size, and you eliminate some of the blockage in the port. And the cross, and just so you know, the cross counts work very well. It is toggling, and is toggling within the range, within the required range of the calibration. We have to put doors in these manifolds when you go to clean them up. And for example, there is a door that is welded shut. We TIG weld those, and we try not to get a whole lot of material piling up in the log. You have to get, at least my experience has been, 2 doors on the passenger side, 1 door on the driver's side. And there are certain runners, and the ones that I showed you or pointed out to you in the beginning are the ones that we really need to access. There are 2 of those runners that we do not need to access because their slip fits into the log. Yes, and I think we went through that. These pictures, I'm just trying to depict a concept here, not necessarily something that says this is exactly how this should be done. Also, by the way, when you go to welding on these things, you need a cylinder head, and you need an old garbage cylinder head that you can use as a fixture, and the correct fasteners so that you can torque it down and you can gently, slowly heat and work this thing without having it distort. We have some other alignments that we can do. For example, the turbocharger to the intercooler. The big circle is just a representation of a compressor housing. The The small object in the lower left is the top of the intercooler neck. Of course, we know that we have those little brass brackets and the bolts on the back side of the compressor. And what we really want to do is we want to make alignment there. We want that gas to flow straight in there, and we want it to be nice and smooth. We don't want any obstruction. That's really important, and believe it or not, you can walk around just at any car meet. I don't see a lot of it here, but you can walk around and you can see people with them 5 degrees out of angle, 10 degrees out. I've seen them all over the place. And the thing is, that's free airflow. That's good stuff to know. We're just basically trying to align, and you can. There's a red line that I have in the center of this. It doesn't show up on the projector. There's a red line there that shows that we're just trying to center line everything so that we can run all of the we can run along that center line. And it's difficult to see there, but the blue hidden lines in the drawing, that just indicates the wall thickness of the housing itself and of the turbo neck. So you can kind of get an idea of that relationship. Airflow gains through the throttle body are possible with a reduction in the throttle shaft diameter. I don't, like I said here, these gains are very small and really probably don't represent a good value on a car with a small turbo. Removing any upper intake manifold overhang in the throttle body airflow can be a good idea, and I have seen some of that. I would not recommend removing the EGR port on the upper manifold unless the cylinder heads are being ported and your software disables the EGR. A move such as cutting that EGR chimney out of the upper plenum will create an uneven EGR distribution condition, and your car will just have a lot of excessive ESC activity or going into knock, which you don't want to have. Let's talk a little bit about what happens to us when we have to go get some work done. Who do you trust? Folks in our club have asked, where do I get my engine work done? And there's good and bad responses depending on names, and people have favorites, and we don't want to go there as far as names being good, bad, or indifferent. But it's all about capability. It's all about proper equipment. It's all about a skill set, communication, and the correct specifications. There are shops that do inferior work, but yet have 5-axis CNC machining centers. My own personal experience, I used to go to a shop in Flint, and they had equipment that, well, you can read it right there, that David Dunbar Buick himself would have spit on, but yet this work was tremendous. Their work was very precise and was very accurate. A line bore for a turbo V6 is just like any other engine. It's the level of detail and the process required that drives product quality. If I get a line bore where the caps and the block was not distorted the correct way so that when the line bore was processed against that block, and then I replicate that when I put that block back into my car, my line bore goes out. It's just that simple. Communicate well with the shop and know what's required. Be prepared with the proper specifications and understand how they will relate to the build. I personally have no business bringing my performance engine or performance parts into a shop and not being able to converse properly and correctly with the person that's going to do the work. Basically, I'm not going to go in there and ask somebody to build me something that I cannot talk to them about intelligently. That makes no sense. The shop needs to assure that the work will stop when choices or issues arise which deviate from the original intent. We have a program. I'm walking in with my engine block, my crankshaft, rods and pistons, and I'm asking this shop to refurbish my short block, and I'm asking for a short block that will stand up to 600 horsepower reliably. What does that mean? How do I deal with that? How do I relate to that shop? What is that shop doing for me, and what is my information set with respect to, this is what I think I need. Is this indeed what I need, and how do you propose to do that? Communication. I I watched, for example, as a beautiful set of 8445 heads that were ported to the max, and they moved the number. These were over 200 CFM on the intakes. They were basically compromised because the heads were brought to one shop. They installed these gasket receiver rings. What they do is they basically squish the gasket down. The engine had a problem. It was taken out. The owner was not happy. The owner chose another shop. So by the time the owner got the heads and the whole engine into the other shop didn't agree with the first shop. And that shop basically said, why are you putting these grooves in here? Or why are these grooves in here? They're going to cause damage to the cylinder head gasket and cause chamber leakage. And basically, the owner of those cylinder heads basically said, well, as a matter of fact, he was at work and he was under there were a lot of things going on at that time. He said, go ahead and do it. Take them off. Little did he know that those receiver grooves were 32 thousandths below the deck. So these cylinder heads were shaved 32 thousandths for no reason. I guess what I'm trying to suggest here is that we like to deal with one shop if we can. The shop also needs to furnish those details in terms of what the build sheet is, or what the build specifications of the engine are. At engineering, we had blue builds, we had green builds, we had all of the critical numbers depending on the usage of an engine, whether it was going into a cell for dyno durability, whether it was a development engine. Those numbers needed to be known, because now all of a sudden, here's a guy, an engineer or a person, whether they're out of Mesa or at Milford or wherever, and they have a motor and it has a problem, and they have to have information, whether that information is on a database, whether it's in somebody's binder, wherever that information is, they need to have that data. Us as owners of these cars, when I get a short block or I get an engine that's been processed in a machine shop, I need to have that information back. So that's something that the shops need to belly up to as well, is to provide that information to the owner community so that they at least have the bearing clearances and a few of these other critical clearances, so we can understand and see what was done. Because a lot of times we get a receipt for a new short block, $5,000. Well, what happened to that short block? How did you process it? What was done? What are the clearances? And if we don't have that information, hey, we're just hanging out in the wind. The bottom line, and this is really the bottom line, and this is all predicated on a properly running engine. Number one, exhaust back pressure is not your friend. We have plenty of back pressure from a turbine wheel, from the inertia of the turbine wheel. Exhaust system improvement by shedding flow resistance without losing flow velocity is the way to more air out of the engine. Induction enhancement, number two. More cool air in because more hot air is going out. Improved charge air cooling with pressure drop awareness. A stock intercooler neck change allows for improved volume at lower pressure drop across the core. I don't want to name anybody who's done this, but you probably all know that's the Duttweiler neck. A fuel system capability is imperative. A fuel pump with volume capability in the 70 PSI range and injectors to match. Typically, we're running cars at 3 bar static fuel pressure. So now if I take that fuel pressure and add it to the boost pressure, some of these guys are running 68, 69, 70 PSI. Typical single fuel pumps in this day and age are falling away. Now what happens is I lean the motor out. Bad news. If I don't have all that 116 VP octane in there to try and save my valves and everything else, I am headed right back to the shop, and I might be out there with a shovel trying to dig the mains out of the pavement. So the bottom line is I need gas, and I need the right type of fuel, and I need the right injector capability so that I am not running out of injector and running out of fuel for the car. Because we can bolt these big turbos on these cars and we can push a ton of air to them. But if we can't fuel them, might as well stay home. Engine controls and I'm talking about a calibration, and that's a real general word to use, but a proper engine calibration that's going to do the job, an adjustable fuel regulator, a knock detector, a fuel pressure gauge, a boost control gauge, and a scan tool or a logging tool of some sort so that we can understand what our data looks like. When we start to tune the car, we have to understand where we are. If we don't have data, it's like, hey, here we go again, the blind leading the blind. And that's how we have accidents. We have guys in our organization or in this club that are running in the tens with stock caps, 109 blocks, and they are running, I wouldn't say they're running every weekend, but they've made a lot of passes on these motors. And I'm talking about trap speeds of about 125 miles an hour in a 3,500-pound car. You say, how do we do that? It's real simple. We control our fuel. We tune for no knock. That's the big deal. Pump gas is not consistent. Station to station, I would be willing to bet if I went out and I could measure specific gravity on pump gas today, and I went to BP and I went to Sunoco and I went to Marathon or wherever I went, I would find that that fuel had different specific gravities. So the concern is do I anticipate now that I have this octane, and now when I go ahead and I say, well, I'm using alcohol that's been sitting in my garage for 6 months, how do I know what my octane really is? How do I know that I can fuel this car? So that's a big question, and that deserves serious consideration. Number 6, boost is not power. The gauge pressure that we are reading, and that's exactly what it is, a boost gauge, you are reading gauge pressure of the gases moving through that tube. That is not what is going to give you power. What is going to give you power is the cubic feet per minute through that tube. And because of that, well, it's pretty straightforward. Boost is not power. Airflow is a reflection of potential power. It's time to choose. The fuel cheater alky or race fuel. The more time spent in the power area of a torque curve is critical to making the car run well. We typically have cars that are running in the 53, 5400 RPM range at a shift point. We have some that are running much higher. I guess my contention is where the cam and where the engine is making power, we want to stay in about a 600 to 700 RPM, maybe an 800 RPM bandwidth of that on shifts. The longer I can keep the car in the top pier, the top envelope, if you will, of the torque curve, I'm going to run faster. I'm utilizing my power better. A taller tire may be your friend. Think about it. If I have the torque to move that tire and I can put a taller tire on that car, the car is going to go faster. And that's it.